We knew all about the adult individuals, but we didn't know much about the children.
The brains of baby chimps have an early growth spurt. They're almost fully formed by age 3. In humans, that growth spurt is slower, and it takes nearly 2 decades for our brains to fully mature. But what about Salam's brain 3.3 million years ago?
But of course, most exciting.
Her skull tells us all we need to know. We have her milk teeth and her adult teeth, which give us her age, 3 years old. And we have a cast of the inside of her skull, which tells us about her brain.
When you have this, you can directly measure how much of the brain was formed at age 3.
From other fossils, we know how large Salam's brain would have been as an adult. So Zerai could calculate how much of her brain was already formed by age 3 when she died. He knows what the answer would be for a chimp.
By age 3, a chimpanzee would have over 90% of the brain formed.
But Salam's brain was only around 75% of its adult size, suggesting it was growing up slower. Childhood would have been her time to learn the survival strategies her family group needed to live in a dangerous world. Perhaps this set the stage for our longer human childhood when culture is handed down. But is there any other evidence Salam's brain was becoming more human and less ape? To find out, compare a human brain to a chimp's.
This is the brain of our closest relative, the chimpanzee brain. Slightly larger than you would expect of a typical primate for their body size, not greatly so.
Scientists look for clues to the evolution of the brain in the folds and furrows on its surface. One important structure is called the lunate sulcus.
In chimpanzees, as in many primates, there's this big, deep sulcus here, the lunate sulcus.
The lunate sulcus is a deep furrow in a primate's brain. It divides parts of the brain related to vision from the rest of the neocortex, which is where more complex thought happens. The human brain doesn't have this deep furrow, and the neocortex is bigger than the vision structures, which have moved far to the back. So did Salam have the deep furrow and small neocortex of a chimp, or had something changed? Brains don't fossilize, but her remarkably complete skull provides a way to see some of the different structures of her brain. A cast of the brain case, called an endocast, preserves the impression of the brain's surface. Ralph Holloway has a collection of 300 brain endocasts from many of our ancestors.
What a paleoneurologist like myself will be looking for are those indications on the endocast that might suggest reorganization taking place. And that's why things like the so-called infamous lunate sulcus becomes important.
Ralph claims that as chimp-like ancestors evolved into creatures like Salam and Lucy, the lunate sulcus, the furrow marking the vision structures, moved back, making room for a larger neocortex, the thinking part of the brain.
If you look carefully, what you've got here is a depression that could very likely be the lunate sulcus. And so that suggests then by Australopithecine times that you're having a beast that is simply smarter than present-day chimpanzees.
If that's the case, although still the size of a chimp's, Salam's brain had been rewired. But there was a long way to go. She and her kind were still very ape-like. It would take another 1,000,000 years for the seeds of humanity contained in Salam's tiny frame to bear fruit. It's a time still shrouded in mystery. For almost 500,000 years, the fossil record is virtually silent. But in this blank period, something is happening. In 2.5-million-year-old layers, scientists begin to find something new. We might be tempted to call them rocks, but someone was shaping them. They are the first stone tools.
The way we know this is a tool instead of just a broken rock is that it's broken in a very particular way, breaking a flake off this way, this way, back and forth. So there is a method behind how this rock was broken in order to make it into a tool, and it's not a random method.
It's considered unlikely they were made by Australopithecus, Lucy's kind.
Australopithecus was around for a couple of million years and did not make stone tools.
But if not Lucy's kind, then who? The gap in the fossil record makes it difficult to say. But that's not surprising. Tools preserve easily. Bones, much less so. Finally, the skulls of a new creature begin to turn up. Is this the toolmaker? The skulls are different from what came before. They represent the dawn of a new era, beginning around 2 million years ago. This is our era, the era of the genus Homo, humans. The mysterious toolmaker, Homo habilis, is the first of these new creatures.
But we definitely have evidence that the stone tools were being used to break the long bones in order to get to the marrow inside the long bones. There were clear cut marks on the bones of turtles, crocodiles, big antelopes, little antelopes, even hippos, really big animals like hippos. So we know that meat had become a new important part of the diet of Homo habilis.
The first fossil to be called Homo habilis included 21 bones of the hand and was nicknamed Handyman.
This little bone is the bone at the end of the thumb. And that little bone in Homo habilis, like in humans, is very broad. And the broad bone reflects having a broad pad on the thumb with a lot of surface area for fine precision grip.
With newly dexterous hands, this creature could make better tools. But what was it like? The few skeletal bones that have been found indicate a creature much smaller than us, about the same size as Lucy and Salam's kind, Australopithecus, 3 to 4 feet tall. Homo habilis was still ape-like in many ways, but with a critical difference.
What we see in the evolution of Homo habilis is an expansion in the brain size compared to Australopithecus. So here is the skull of Australopithecus, and it has no forehead. It just has a straight slope behind the orbits. Whereas here in Homo habilis, you see a sloping, elevated forehead. And in Australopithecus, the area behind the orbits is pinched in, also reflecting a small frontal region. In contrast, in Homo habilis, we see an expansion of that area behind the orbits that points to an expansion in the cognitive capabilities of higher functions, of higher reasoning functions of the brain.
It was an expansion equivalent to a doubling of brain volume.
Once you go from something like 400 cc's in Australopithecines to, say, 700, 800 cc's in Homo habilis, yes, you're getting a big increase in cognitive capacity.
And along with his bigger brain, Homo habilis was starting to look a lot more human. The contours of fossil skulls allow reconstructionist Victor Dieck to reveal the faces of early human beings. Gone is the projecting snout of an ape. In Homo habilis, the face of humanity is emerging. This poses a great enigma. Why, after millions of years of flatlining, did brain size and mental capacities suddenly take off? Two million years ago, what jump-started human evolution? Scientists all over Africa looked for clues. Here in Kenya, they found some. At the southern end of the Great Rift Valley. It's a hotbed of tectonic activity, where ancient layers are forced to the surface. 10 million years ago, Africa was a much wetter place. A tropical jungle which has been slowly drying out ever since. But these rocks in Kenya show that Africa's gradual drying trend was punctuated by bursts of wild climate fluctuation. Rick Potts is an expert in reading the rocks.
This layer right here represents about 1,000 years of environmental stability, but then we had an abrupt volcanic eruption, and then the lake was around for perhaps 500 years before a drought, and then the lake came back. So in some cases, we saw this through layer after layer of environmental change.
With his trained eye, Rick could see some layers were once lake beds, others desert sands. Still others came from volcanic eruptions, a snapshot of 1 million years of climate history. This observation led him to an amazing new idea: rapid change as a catalyst for our evolution.
And I began to think that, well, maybe it's not the particular environment of a savanna that was important, but the tendency of the environment to change.
Could it be that the need to survive violent swings of climate made our ancestors more adaptable? A group of scientists has come here from Germany to find out just how radical these swings of climate really were. It's hard to believe, but these huge rock formations are made of the shells of tiny one-celled organisms called diatoms. There are many different kinds, but they all live in water. Their shells collect in layers of rock that pile up over millions of years, proving that this whole valley was once a giant lake. Annette Junginger analyzes these rock samples under the microscope.
What I've discovered was that those white layers consist of a special kind of diatoms which only live in deep lakes.
But between the white layers, she also finds other species of diatoms which only live in shallow water. It means that in this spot, a massive lake appeared and disappeared and reappeared many times.
These lakes are really significant. These are not small little ponds. And what we've been able to document now is a series of lakes that are cycling.
When we're talking freshwater lakes, the size of Lake Victoria, filling the whole Rift Valley and then disappearing.
An enormous amount of water rushing through this area.
This constant flux of turnover, of change.
An awful time to live here.
It's not just a unidirectional change, it's going back and forth.
Against the backdrop of a slow drying trend, Africa was periodically